Well, thank you, Alex, for the introduction, and thank you all for being here. I know it's Friday afternoon, so I will try to finish before 5:30. First, hello. My name is Emina, and I'm an assistant professor at the University of Washington in the computer science department. I am here today because, like everybody in this room, I love functional programming and, of course, parentheses. So what I'm going to talk about today is a new programming language that has plenty of both. It is based on Racket, which, as Alex said, is another Lispy language. And in particular, what Racket is very good at is essentially being a programmable programming language. It allows you to very easily create new programming languages, in particular new domain-specific languages. So basically, you can use Racket to package your insight and knowledge about a particular domain of application and allow other people to efficiently solve problems for that domain. Now, once you've created your language in Racket, your DSL, you might also want to create some tools that allow people to use your language more efficiently. For example, an automated test generation tool, an automated debugger, and so on. So the language that I've been developing for the last 4 or 5 years on top of Racket allows you to build a specific class of tools that are based on program verification and synthesis. So the language itself is called Rosette. And if you're not familiar with the verification and synthesis tools, don't worry, everything is going to be clear by the end of this talk. But at a very high level, you can think of verification as solving a problem of checking that a program satisfies a specification on all inputs drawn from some either very large, so exponentially large, or even infinite set, right? So you can think of it as exhaustive testing on steroids. Program synthesis solves kind of the complementary problem, which is somebody gives you a high-level spec, and you can use program synthesis to actually generate code that implements that spec in your DSL. These tools are based on state-of-the-art automated theorem provers, which also go by the name of SAT solvers, satisfiability solvers, or SMT solvers, so satisfiability modulo theory solvers. And for that reason, in addition to being a programmable programming language, by virtue of being embedded in Racket, Rosette is also a solver-aided programming language. Now, as I said, all of these words are going to become second nature to you by the end of this talk. But before I dive into telling you what Rosette is and how you can use it to do cool things, let me briefly motivate this work. Why it is that, I've spent the last 5 years of my life working on this, what's exciting about it, and what it is, what are the kind of cool things that you can do in the real world if you had access to this technology, to verification and synthesis tools that are based on automated or push-button theorem proving. All right, so normally when you think of programming, you think of it as a task that is performed by professional software developers, right? Essentially the people in this room. It turns out that in the real world, pretty much any kind of a knowledge worker needs or wants to do some kind of programming. They have a bunch of tasks that they want to automate. So let me give you a few concrete examples of people, or the kinds of people of whom you may not think of as programmers, but who actually do need to do some programming tasks, and how we can help them with this verification and synthesis technology. So our first little guy here is a social scientist. So today's social science involves essentially collecting and analyzing huge amounts of data. Now, before you can do anything useful with your data, you have to massage it into some kind of a standardized format. If you know how to program, that's easy. If you don't know how to program, you put it into an Excel spreadsheet and you transform each one of them by hand, right? This is very painful. Essentially, what these people would like to do is demonstrate on a few examples how to perform the data transformation and have the computer synthesize a program that will perform the rest of the transformations. Now, another kind of person whom you may not think of as a programmer are biologists. So what they would like to do is create executable models of biological processes. And the reason why they would like to have these models is because they can essentially cut the amount of time and the expense that it takes to conduct experiments in the wet lab. A particular kind of biological models that they would like to have are essentially models of diseases or models of processes that lead to diseases. The way that they would like to create these programs is not by writing Python or even Clojure code or Racket code. What they would like to do is give some system input-output examples. Here is a mutation that I performed on my model organism, usually some kind of a worm, and here is the outcome. The organism died, it was malformed, and so on. Given these input-output examples, synthesize an executable model of a protein network that is consistent with the data, that explains it. Moreover, if there's more than one model that explains it, if there are multiple ones, tell me what next experiment I need to run in the wet lab to disambiguate between these two competing hypotheses. This is a huge deal in biology. For us, running experiments is easy, right? It's cheap. We write some code, we press a button, it runs in a few seconds. For biologists, running an experiment is really expensive, really hard, and takes a lot of time. So anything that we can do to help them make this process more targeted is extremely useful. So this is how program synthesis can help biologists. Now, our final example is hardware engineers or architects, computer architects. So these days, what they spend their time doing is creating new hardware that's more parallel and more energy efficient. Now, creating new hardware is great, but if you want anybody to use it, you have to make it programmable. You have to provide things that people expect, like cache coherence protocols and memory consistency models. Getting these things right, actually creating a correct cache coherence protocol or a memory consistency model is extremely difficult. For memory consistency models alone, right, getting the x86 model, for example, formalized took 4 years and 10 papers at programming languages at formal method conferences. This is how hard it is for experts to do this by hand. So what all of these examples have in common is that people have, in fact, built verification and synthesis tools to help knowledge workers in these domains. However, the gap between the knowledge workers and the tools that they need is huge because it takes so much expertise and so much time to build just one of these tools. In fact, if you build it and it scales and you're successful, you'll get a PhD. At the very least, you will get a paper at a top academic conference. That is how much time and expertise it requires to build just one of these tools. Clearly, if you want to make this kind of technology accessible and available to a wider range of people, to a bigger range of domains, we have to make the process of building these tools easier. And this is basically what my research is about. I work on a new class of languages, so solver-aided languages, Rosette is one of them, that make it possible to build these advanced automated tools, reasoning tools, without having to get a PhD and without having to become an expert in automated theorem proving. In fact, all you need to be able to do is program. The youngest user of Rosette that I know of is a high school student, and he used it to build, for example, a state-of-the-art verifier that can tell you whether a type system that you developed is sound, which is pretty cool. So for the rest of this talk, what I'm going to do is first I will talk about what solver-aided tools are. So I've given you two examples, synthesis and verification, and I will define these things a little bit more formally, and I will show you what it takes where I will discuss what it takes to actually build one of these things by hand. Then we'll talk about how things get better or easier when you have a solver-aided language. In particular, I will show you how to use Rosette to build advanced automation, so verification, synthesis, and so on, for a very simple toy language. Of course, this is a talk that's going to last for 40 to 50 minutes, so it's going to be a very toy language. However, the same process, the process that I'm going to demonstrate on this toy DSL, is what you can use to implement a synthesizer verifier for real programming languages and solve real problems in the real world. And this is what the last part of the talk is going to be about. I will briefly tell you about some of the more recent applications of Rosette to a wide variety of problems, from verification of safety critical systems to super optimization for low-level machine code, ARM code, and so on. All right, so let's start with solver-aided tools. What are they, and how can they help you create better code, so more correct software? Now, normally when you think about writing code, normally when you think about the act of programming, the picture looks something like this. You have a programmer. He has a specification in his mind, some high-level intent that he wants to translate into code. So he will write a piece of code that hopefully implements the specification. So what's the first thing that you do after you write a piece of code? Exactly, you have to test it, right? If you have no other means to tell whether your program is implementing your specification, of course you're going to test it. So what is testing? Well, you basically write a property about your program, a property of your code that needs to hold. So here I'm just giving it a really boring name, safe. The safe predicate returns true if P produces a correct output on a given input. And what we have here is a test case. It basically tests that P behaves correctly on one particular concrete input out of many. Now, when you bring an automated theorem prover into the loop, something interesting happens. You can ask questions about the behavior of programs on all possible inputs. So here's what that might look like. For example, we can ask our solver to search for an input, if one exists, on which the program fails to satisfy its spec. So basically this assertion fails. The way that we do that, and this is important, and this is basically what's hard, is by essentially expressing the semantics of this program as a formula in some logic, usually first-order logic. Now, if you remember, if you've taken a logic class or a discrete math class or something like that, you might remember what these symbols stand for. But essentially what's happening here is that this box in the middle acts as a compiler. So instead of compiling your language to x86 or machine code or another programming language, you're essentially compiling it into logical constraints. So once you do that, once you have the encoding of the program semantics as a logical constraint, what this thing in the box says is there exists an x, so that's the exist symbol, such that it is not the case that P is safe. If this formula has a solution, and the solution here means there is a concrete value for the variable x, which you can substitute in there. So if this formula has a solution, that solution is a concrete test case, a concrete input on which your program fails. So this is how all modern program verification tools more or less work. They take a programming language, they express its semantics as a formula, and then they ask one of these automated theorem provers to answer a query of this form about this program. If the solver finds a solution, we will lift it into values that are meaningful at the level of programming language. So for us, it's going to be a concrete integer, let's say 42, so P fails on 42. Okay, so you've written a piece of code, you've asked your verifier whether it's correct with respect to your spec, and it says no. It gives you concrete input such that if you run P on this input on 42, it's going to fail this assertion. What is the next thing that you do, or the first thing that you do once you have a failing test case? What do you have to do? Debug it. You have to localize your fault first. It turns out that a solver can help you do that as well, and we do that by using the same trick. We are going to express the semantics of this program again as a formula in some logic, and we are going to ask the solver whether this formula has a solution. So the verifier just told us that P is not safe, so the negation of safe P is true on x is equal to 42. So what do you know about this formula that I'm showing you on the slide? Does it have any solutions? Is it true? No. So you would think that, I'm feeding the solver a formula that has no solution. We call it an unsatisfiable formula, that it can't say anything useful about it. It actually can. What it can do is it can isolate a smallest subset of this formula, which by itself has no solution, right? So normally these translations are huge. When you take a piece of code and you translate it into assembly, it's going to be a lot of assembly. Same thing, when you take a piece of code and you translate it into logic, you get hundreds of thousands or millions of constraints. The solver can actually identify just a few of them which are responsible for this thing having no solution. And when you map those constraints back to the level of the program from which they were produced, what you will get is a minimal set of expressions in the program such that you have to change at least one of them to make the program correct. So this way, solvers can also help with fault localization. All right, so we localize the fault. Now we have two choices. If we are super lazy and for whatever reason, it's okay for us to call an MP complete procedure at runtime, don't do this. But let's say it is, we could actually choose to repair this program at runtime by using the solver as a runtime oracle. So I'm going to replace my buggy expression with a call to this magic function choose. And the semantics of this function is at runtime, when it's called, it will return a value such that all the assertions downstream are going to pass. So you can think of it as programming with a clairvoyant oracle. There are actually cool applications of this. You can actually build cool logic puzzle solving engines with this, and in that case it's actually okay to use the solver at runtime because they can scale well enough for this thing to be fast. Obviously, if you're doing it on real code, it's going to be much, much slower. So what we really want to do instead is repair this program statically. To do so, we're going to replace our buggy expression with these double question marks, and I'm going to use these to denote a hole in the program. This hole says to the underlying system, find me an expression in this programming language that I can plug in, if one exists, of course, and put it instead of these double question marks such that the program is correct on all possible inputs. And again, we're using the same trick. We're translating the semantics of the program to a formula, and then we're saying there exists an expression E in our language such that when we specialize the program P with E, so we plug in E for the double question marks, then for all x, P of x is safe. So this is how all of these tools work in principle. The thing that's really hard, you will notice that every time I explain how one of these tools work, I basically have to tell you that you need, in order to get this to work, you need a compiler from programming language down to a constraint system. And this is extremely hard to build. I mean, building any kind of a compiler is hard. There's no reason why building this kind of a compiler would be especially easy, and in fact it's not. This is what takes an enormous amount of time and an enormous amount of expertise. So what Rosette saves you from doing is essentially it saves you from building this compiler. Instead of having to compile the semantics of your language to constraints, all you need to do is you implement an interpreter for your language. Everybody knows how to do that. Or, if it is an embedded DSL, you implement it as an API or a library. The catch is, you have to implement it in a host language, such as Rosette, which is itself solver-aided, and then you will get the translation to constraints for free. So essentially what Rosette is doing, it's taking an interpreter for your language, a program running on top of that interpreter, and translating both of those things to efficiently solvable SMT constraints. It does this magic with the help of something called the symbolic virtual machine. This is the thing that is capable of translating essentially the semantics of your language as given by the interpreter and the program in your language to constraints. And this solves a hard technical problem. I mean, I already told you that just building a compiler for one programming language is really hard, right? What I'm now telling you is that I have a compiler for programming languages. So that was the hard technical problem solved by Rosette. I will not go into details about exactly how this works, how the symbolic virtual machine works. You can find it in our papers, and of course I'll be happy to talk to you offline. So what I'm going to do instead is I'm actually going to tell you how to use Rosette to build these tools without having to build these compilers. Before I do that, let me briefly talk about what I mean by domain-specific language, what I mean by DSL in the rest of this talk, why we're focusing on DSLs, why are they interesting, and then we'll see how to build one. So normally, we build DSLs by layering them on top of general purpose languages. When I say a DSL or domain-specific language, I mean a language that is specialized for solving problems in a given domain. Usually, not always, usually they're also limited in capacity in some way. Most of them, or many of them, are not Turing complete, for example. You create one of these things in one of two ways. You can do what we call a deep embedding of a DSL into a host language, and that essentially means that you're going to write an interpreter for your DSL in a general purpose host language. The other approach to building a DSL, and this is a very popular one, in fact, almost all the talks that I've seen today, they were either building DSLs, whether they called it this or not, or they were using DSLs. So the second approach is to essentially build an API or a library. If you really think about it, a well-designed API gives you a language. It gives you the right abstractions, the right operations in those abstractions, the right concepts to solve a class of problems. So building an API, the act of building an API is the act of essentially building an embedded DSL. So to give you some concrete examples of all of these things, general purpose languages that are very good for building DSLs, Scala, Racket, Clojure, JavaScript. And of course, everybody in this room has used or at least heard of at least one of the DSLs that are here on the slide, right? Just about any domain that you can think of, there's a DSL for it. Why? Why do you think people would bother with DSLs? I mean, clearly, anything you can do in a DSL, you can do in general purpose languages. Because a general purpose language is strictly more expressive, usually. So why bother with DSLs? Well, the DSL is the ultimate abstraction for solving a problem. So let me give you a concrete example, a code example. So what you see here is matrix multiplication expressed in a linear algebra DSL, right? Like MATLAB or Eigen. and matrix multiplication expressed in C or Java. So the difference is obvious. When you're working in a DSL in a language that provides the right abstractions for solving problems in a given domain, you're going to write far less code. This is great. It means that you're more productive and you're also less likely to introduce bugs. Fewer code, fewer bugs. The other thing that's really important here is that DSLs are very good for tools to operate on. If you're building a compiler for a DSL, for example, an optimizing compiler, it can take advantage of the properties of the domain that are not obvious or would be very hard for a general purpose compiler to infer. For example, a MATLAB compiler can take advantage of the fact that matrix multiplication is associative. There's just no way that the C compiler can figure that out from these three nested loops. So DSLs are good for people because they narrow the gap between what you want to say and how you say it. And they're also good for tools because they allow the tools to take advantage of the domain properties. In this case, matrix multiplication. And this goes for all tools, not just compilers. It goes for verifiers, for synthesizers, and so on. So a solver-aided language stack looks just like a normal language stack, except that it's running on top of this non-standard virtual machine. That's basically the main difference. One solver-aided host language that exists, actually the first one that was developed is Rosette. A few other ones have been developed since then, but we will focus on Rosette here because that's what I know best. And some of the solver-aided DSLs that have been developed in Rosette, as you can see, they cover a huge range of domains. So this is just a few recent examples. There's a DSL for spatial programming, for intelligent tutoring, for memory models, and so on. I will talk about some of these in more detail towards the end of the talk. Before we do that, though, let's talk about Rosette itself. Let's see what it is that it adds to Racket. And if you wanted to build a solver-aided host language for your favorite language, Clojure, what would you need to add to it? Well, it turns out that all you need is 6 constructs. Just 6. And it's these. I will explain what they mean. I will walk you through their semantics as we go through an example. But I think for some of them you can already guess what they do. Assert does what you think it does, right? It takes a predicate and checks whether it's satisfied. The lower 3 essentially are making the tools that I talked about, verification, synthesis, and so on, into language constructs, first-class language constructs in this Racket language. And the first one is probably the least familiar, and that is the one that we'll introduce by example. So what's going to be our example? Well, we're going to build a tiny, tiny solver-aided DSL. It's going to look a lot like assembly code. I'm going to call it BV, which stands for bit vectors. You can imagine that you would use this to develop fast, low-level libraries. So here's an example of a BV program. This program takes the maximum of 2 32-bit integers without doing any branching. And the operators do what you probably imagine that they do. So BVGE checks whether the first argument is greater than or equal the second argument. BVNeg is the arithmetic negation. XOR and are bitwise, XOR and AND. Okay? So this is what a program in the BV language may look like. So what do we want to do with programs in the BV language? Well, obviously, we want to be able to run them and test them. We want to be able to verify them, debug them if necessary, and synthesize repairs if needed. So this is what we want to be able to do by the end of the next 10 minutes. And here's how we're going to do it. We will implement an interpreter for BV in Rosette. It's going to be about 10 lines of code. and we'll get everything else more or less for free. So let's see how that works. I will show you how the interpreter for BV works by demonstrating its operation on this particular example. So we are applying BV max to the inputs -2 and -1. So the first thing that happens, of course, is we're going to parse this code. We're going to parse it into this extremely simple representation that I'm using here. So a program is a list of lists, and each of the lists represents an instruction as follows. The first number in the list is the identifier of the output register to which the instruction is going to write its output value. The second identifier, so the symbol, is the name of the instruction that we're going to execute. So this is our opcode. And the remaining values in this list are the identifiers of the input registers. So this is where the instruction is going to draw its input values from. So it's a super simple representation. There's nothing tricky about this. So here's our tiny little interpreter. So it's going to take this AST, abstract syntax tree, and it's going to take our input and it's going to do the following thing. The first thing that it does is it creates enough registers to run this program. And because our representation is so simple, it's basically the length of the program representation. And it's going to populate the first n registers with the n inputs to the program. All right? Then is going, for each instruction, is going to execute it as follows. We are going to use Racket's pattern matching to bind the local variables out, opcode, and in to the corresponding, we're going to deconstruct this list, to the corresponding elements of the list. So the out variable for the first instruction is going to be bound to the value 2. The opcode is going to be bound to the symbol BVGE. And in is going to be bound to the list 0, 1. The next thing that we're going to do is we're going to use eval to evaluate the opcode and grab from the environment the procedure object that corresponds to this opcode, right? So it turns out that Rosette actually exposes these bit vector operations. It turns out that people who work on solvers and automated theorem provers really love these low-level things, so we expose them. And when you do an eval of an opcode here, you will get a procedure that will behave as you would expect. The next thing that we're going to do is we are going to load the values from the input registers into this arguments variable. This is our local variable. So now args contains the actual values to which we want to apply our procedure. So the last thing that we're going to do is we're going to apply the procedure to the arguments and store the result in the output register. We're going to do this for every single instruction. And the result of the program, the result of this evaluation, is going to be the value that's stored in the last register. So this is it. The reason why I'm showing you this code is not because it's complicated, it's quite the opposite, right? I'm showing you this code to show you that it's actually something really simple. If I had asked you to build an interpreter for such a low-level language, you might write something like this. It will probably take you 10 minutes. Now, this is not interesting or complicated from the point of view of a programmer. However, note that this interpreter is using all sorts of advanced programming languages features, right? So it's actually using pattern matching in Racket, it's using first-class procedures, it's using eval, it's using high-order procedures, it's using side effects. May not seem like a big deal to a programmer, as I said, but this is what makes people who work on verification and synthesis cry. We cry when we see this. These constructs are incredibly difficult to translate to efficient constraints. Some of them we don't even know how to translate. However, I'm letting you use it. I'm letting you use all of these. And if you do have some background in compilers, part of the reason why this works is essentially partial evaluation. Most of the time, we're able to partially evaluate away the constructs that are not translatable to constraints. All right, so Here is our interpreter for the BV language. And when we interpret BV max on the input -2, -1, you get -1 as expected, right? So all seems to be good. But is it really? Well, we can see whether this program is indeed correct on all possible 32-bit inputs by verifying it. So here is what the interface for verification is going to look like for the BV language. So the verify form or the verify construct at the BV level is going to take two inputs. The first one is the implementation, right? So the thing that we want to verify. And the second one is a reference implementation, which is going to act as our specification. I'm not showing what max looks like on the slide here, but you can imagine that it is the obvious implementation of max, which uses a conditional, right? So here I'm using another program as the spec. In fact, the beauty of doing all of this in Rosette is that your notion of a spec is extremely flexible. You can write constraints, you can write assertions, you can use a reference program as your spec. So what we're going to do now is we will see how to implement this verification for the BV language by using the verify construct that Rosette adds to Racket. Along with these two other constructs, define symbolic and assert, which all of you know what assert does. So let's talk about define symbolic now. So what this thing here does, it basically creates two fresh symbolic constants of type integer, and it binds them to the two local variables n0 and n1. So what's a symbolic constant? Well, it is a value of type integer, and this is the only thing that the runtime knows about it. It knows that it's a value, it knows that it's an integer, but it doesn't know which integer. The solver will eventually decide which integer these two need to be in order to try and violate an assertion if that is possible. So as far as you're concerned, you as the programmer, the value of this particular integer is unknown at compile time, it's unknown at runtime, it actually only becomes known after solving. But you can use it in the same way that you use any other value of the same type. You can put it in a data structure, sure. You can put concrete integers in data structures, no problem. You can apply arithmetic operations to it. You can pass it into your own procedures that you wrote, such as interpret, no problem. You basically just treat it as a normal integer value. Finally, in order to implement our verifier, we're going to use this verify construct here in Rosette, which Rosette provides. And the semantic here is the following. Verify expression here, expression can be an arbitrary expression in Racket, it can call other procedures, it can contain many assertions, but conceptually, what verify does, it executes all possible paths to this expression. Obviously, it does not really do that. It performs symbolic reasoning, but conceptually, it will execute all paths through this program, collect all the assertions that are encountered along these paths, and ask the solver whether there is a binding of concrete values to these that can replace these symbolic values n0 and n1 such that at least one of the assertions encountered during the execution of the expressions is violated. So this is the semantics of verify. And this is how you can implement verification for this BV language without actually ever interacting with the solver directly yourself, right? You're just using the corresponding constructs in the host language to implement verification for your own domain-specific language. So it turns out that I made a mistake somewhere when I wrote this bit twiddling routine. And in fact, there is a concrete input on which this program will fail. So the solver says that BV max does not behave as max, so it doesn't actually take the maximum of these two 32-bit integers, 0 and -2. We can check that the verifier is not lying by simply running our code. We have an interpreter for it, right? And when we run BV max on 0 and -2, we got the result -1, which is very clearly incorrect. So what's wrong? Anyone see it? I'm just kidding. We're going to ask the solver to help us with this one. As you can see, even though it's a very small amount of code, and given enough time, you could all figure out what's actually wrong. It would probably take you quite a bit of time. It would take me quite a lot of time too, and I've written it and seeded the bug. So the debug construct is going to be implemented in the same way as the verify construct, by essentially leveraging the underlying construct of the host language. And I'm not going to walk you through the details of the code. I'm just showing you the code to convince you that it is a small amount of code. But at the BV level, the semantics of debug is I'm going to take an implementation, a specification, and a concrete input on which they differ. And the output is going to be a minimal set of expressions in my program, at least one of which I have to change in order to make this program correct. Which one and how do I change it? Well, we're going to ask the solver for help there as well. We're going to replace those buggy registers with a double question mark, and we're going to implement a synthesis procedure for our BV language by using the synthesis procedure from Rosette. Again, we need an implementation, in this case a partial implementation with holes in it, and a specification. And here is the correct program. This indeed implements maximum 2 32-bit integers without any branching. So this is it. This is how you use Rosette to implement verification, synthesis, and so on tools based on automated theorem provers without having to become an expert in automated theorem proving. And trust me, it takes a lot of time to do that. So what I'm going to do now is I'm going to take the remaining time to tell you a little bit about some of the real applications of Rosette, which were built in pretty much the same way as I just demonstrated for the store language, except of course on a much larger scale. So here is a partial list of things that people have built just in the last year. Rosette has been publicly available since 2014. And people have done lots of cool things with it. I will focus on 3 applications that kind of show the range of domains to which you can apply this sort of technology. So the first application that I'm going to talk about is building a verifier for a safety critical system. As I said, I work at the University of Washington, and at the University of Washington Medical Center, they have this amazing machine which is called CNTS, stands for Clinical Neutron Therapy System. This is a machine that treats inoperable and radiation-resistant cancers with neutron radiation. Normally, radiation machines do so by protons and electrons, but some tumors are actually resistant to proton-electron radiation. This guy uses neutron radiation. Why is that significant? Well, it turns out that building a machine that uses neutron radiation in this way is extremely expensive. There are 6 of these in the world. We have one of them. Because they're so expensive, they have to last for a really long time. This machine has been treating patients for over 30 years. The first software controller for this machine that basically controls the machine movements during therapy, and basically a prescription to be treated by one of these things involves a physician writing down the values of 400 parameters that have to be set. And one of the jobs of the software controller, the safety critical part, is that it has to make sure that every single one of those parameters remain within the prescribed limits during treatment. Because if they don't, you're risking radiation overexposure. So this is one of the main safety critical properties the software controller has to maintain. The first version of this control that was installed by the vendor, it was written in Fortran. The engineers who maintained the machine, they rewrote the software controller in C in the 1990s. But very recently, around 2013, in order to support new therapies, they have switched to a programming language called EPIX. Has anyone heard of EPIX? This is the most important programming language nobody has ever heard of. It controls billions of dollars of scientific equipment. If you remember gravitational waves being detected, I think it was last year, that was running EPIX code. It runs everything from telescopes to neutron accelerators to all sorts of advanced machinery. So they rewrote their software controller in EPIX, and they were wondering whether this was correct. Does it still satisfy the safety critical property that it needs to maintain? In order to check this, we wrote an interpreter for EPIX in Rosette, and when we ran it on a pre-release version of this therapy control software, we found a safety critical bug that would have prevented the beam from being shut off when it was supposed to. This bug was so nasty, in fact, the way that we build this interpreter for EPIX is by reading the EPIX documentation, essentially the spec, and implementing the spec. When we found the bug and we gave it to the engineers, a concrete input, a test case, they ran it on their code and they were like, no, this is a false positive by your tool. Our code works fine on this. It turns out that the bug in their code was being masked by a bug in the EPIX runtime. So they had to go through their code and actually fix all instances of this bug before they could upgrade to the corrected version of the runtime. And they are currently using this verifier to check their code every time they add new therapies. Every time they change it, they will re-verify to make sure that it's still safe. So that's one application. Another one is very, very different. There is a nonprofit organization called Enlearn, which is based in Seattle. It's run by one of my colleagues, Zoran Popovic, and Enlearn's mission is to create educational tools that make it easy for little kids, so we're talking grades K through 12, to learn things like math, algebra, and so on. They are using Rosette to automatically generate things like math games, educational math games that have been released they've released to thousands of students, they're being used by thousands of students now, and eventually millions, so that's the goal. What they're working on currently is actually creating a Rosette-based DSL that would enable people who are not necessarily experts at educational technology, so teachers themselves, to build their own tools and their own games that work with their own curriculum. So that's another application. So the final one that I'm going to mention very briefly is a recent application to super optimization. Does anybody know what super optimization is? So what an optimizing compiler does, in order to optimize a piece of code, it will apply a series of rewrite rules to the code, right? So pattern match, rewrite, to essentially make your code go faster. Writing these rewrite rules is really hard, right? I mean, this is why people have taken, decades to build GCC. And getting them right is also really hard. Super optimization, instead of actually creating rewrite rules, we use a theorem prover to search for optimal code sequences. So you give me a list of straight line code. That's going to be my reference implementation. And I'm going to search for the most efficient sequence that implements the one that you gave me, but minimizes some cost according to a performance cost model. This particular framework called Greenthumb allows you to create these super optimizers very fast for very exotic architectures, and the performance benefits that you gain are pretty significant. So for example, It will show up to 82% speed up over GCC03 for the ARM chip when run on wireless and embedded benchmarking suite. So this was a target. This was the application they were targeting. And also it will allow you to create optimizing compilers for new emerging chips that are designed to be very low energy, very energy efficient. So they use a small amount of energy to perform the same amount of computation that a traditional chip would. And all you need to do to use this thing is to essentially write an emulator for your chip in Rosette. And that will give you the verification synthesis part for free, and Greenthumb will do the super optimization search for you. So that's all I have. Thank you very much for your attention, and if you have any questions, I'll be happy to take them afterwards because I'm out of time.